back for more. So let's take a look at B here. Now, B is interesting. I gave you guys a hint. I think only 2 people actually understood or commented on the hint there. So again, going back to what we talked about before, the who, the what, the when, the where, and the why. Okay, so what's going on here? So the who. Well, we've got an aromatic ring. Okay, that's reacting with bromine. That's interesting. And what did I leave out? There's no catalyst, right? So there's your who's. This is interesting. Every other reaction on this page has got a catalyst. This doesn't. So that would be something to comment about, right? But it's another aromatic substitution. We've got a not so great electrophile here, right? Br2 is not a good electrophile. So the what, right? This is our electrophilic aromatic substitution again, right? Here would be a good time to draw the mechanism. Hopefully you guys can draw the mechanism. And really this is the drawing the mechanism here is going to get you to the answer, or a very, very thorough answer. Because let's think about this for a second. Let's do this here. Oops. There we go. Let's do that. Good. So likely the mechanism in this case is going to look something like this. Like this, right? And then go through and draw the resonance structures for these, okay? I'm going to skip it here just for the sake of space. There we go. That didn't take too long. And we got a nice mechanism that explains a lot, right? That gives me a very thorough, concise understanding of what's happening. Okay, do you guys catch what's happening here, though? It's subtle. This is a subtle question. I'm going to admit that. But a lot of answers for this question said, okay, well, 3 bromines are added because there's an excess. Well, that's true, but how are those bromines added? Well, they're added one at a time. You're like, oh, okay, yeah, that makes sense. But you guys catch what's going on here? What happens every time you guys add a bromine? Let's say we went on and did the next step in this mechanism here, right? And then we would go on here, ... right? And we would follow the same set of steps. So we add these bromine stepwise. What is happening? Well, remember, bromine is a deactivator. So that's interesting, right? We have a deactivator that's orthopara-directing, right? So that's something interesting to think about here, right? At the end of the day, we add 3 deactivators to this ring, stepwise. But still we don't need a catalyst for this to happen. Why is that? Well, there's 2 reasons or 2 arguments we could make. One is that we've got a strong activator here. Strong to moderate, whatever you want to say, that's fine, right? Strong to moderate activator. And remember that the bromine does help stabilize the carbocation intermediate. So the more bromines you add, the more we can stabilize that intermediate. Okay? So a lot of information comes out of this what here from simply drawing the mechanism, showing the stepwise addition of those bromines. We understand then about what the activating effect of the ether derivative there, the methoxy group, right? That's important. We think about how each bromine is added stepwise, how it actually ends up deactivating the ring, yet because the ring is still activated enough, we don't need a catalyst, right? Remember what we're essentially saying at this step here, is that this ring has enough of a negative charge to reach out and grab a bromine. That's pretty unusual, right? Usually we have to generate a very good electrophile, right? But this is a good example of what it means to be an activator. We're basically making the ring more negative, and then it can go after weaker positive things. Okay? Now, the when in this case, right, we don't have direct kinetic information, but it could be a good argument to describe there about what we were just talking about, right? What happens and how do each of these bromines get added, right? The stepwise addition. Each one gets added one at a time. Now, we could probably say that the para gets added first and then the two orthos or whatever, and that'd be just fine, okay? The where and the why, right? So I think we kind of covered all that stuff here, right? So notice that when I ask you guys to draw or to discuss those 5 W's, it's not that they're all exclusive, right? They do overlap with each other. But what I'm trying to get across is when you guys have your answers, go through and ask yourself, does this describe the who, what, the when, where, and the why, right? And you'll see that they overlap. In some cases, you can make distinct arguments, and in some, maybe they're going to overlap a little bit, and that's just fine, okay? All right, let's go down here. What is this telling us? So here, again, we see a very similar situation, right? We've got a strong activator and a strong deactivator, and we do a reaction, okay? So we're doing another electrophilic aromatic substitution. We add this to the ortho group right here, right? Ortho to the activator, meta to the deactivator. Great. We've got information about kinetics and major versus minor yield, okay? We notice that the only difference is where we have the deactivator, or the relative position of both of those, right? So what's going on here? Again, you go through and you draw the mechanism. Okay? You go through and you draw the mechanism. And what you'll notice is that for this particular case, really what I was asking you guys to pay attention to was that the yield and the time doesn't change. What does that tell you? Right? This is all about the when question here, right? The kinetics. It tells us a lot. It tells us that the deactivator, the position of the deactivator doesn't affect anything. Oh, that's interesting, right? That's interesting. You see, whether the nitro group is para or meta to our activating ring there, it doesn't change the kinetics in this case. What does that mean? Well, we have to think about the relationship between activators versus deactivators and what step, right? What step of the mechanism do they affect? What does it mean to be an activated ring? Well, it's just like what we talked about up here, right? It means the ring is partially negative, so it's easier to grab, right? It's easier to grab something positive. The directing effect happens after it's grabbed, so to speak, right? The directing effect happens after it's grabbed with the resonance structures that come as part of our mechanism. So it's very interesting to sit here and think about this a little bit, right? What does it mean to be an activator and a deactivator? What parts of the mechanism are affected by it? Okay? Now, granted, like I said, these are just example reactions. Who knows what's going to happen in real life? But I'm asking us to think about, what is the data telling us about the mechanism and the steps and the who, the what, and the when, and the where, and the why, right? So just telling me, the chloro group got added ortho, and then it got added para. Well, that's fine, but explain what that does. Explain how that happens, right? Well, gee, Dr. Eight, that's a lot of mechanisms. I know. It is. That's okay, right? So hopefully this maybe kind of clears up a little bit about what I was kind of looking for with these questions here, right? The who, the what, the when, the where, and the why. Give me a thorough, yet concise and clear explanation for the following observations, right? 5 W's. Okay, cool. So I think we're good with this video here. Only took us about a little bit, like 10 minutes here, right? Okay, so I'll keep going through this. We'll post another video soon here, right?